that get mapped to the zero element in W. So set notation wise, kernel of T is U and V such that T of U is zero vector in W. And the image of T are precisely the set of all possible outputs that T gives you. Again, set notation wise, it becomes T of U such that U is in V. And this is also denoted by T of V. So like I said, these both happen to be subspaces. The kernel of T is a subspace of the domain V, and the image of T is a subspace of the codomain W. Now, I'll prove one of these for you, and I'll leave the other for yourself. Which one would you like me to prove for you? Any preferences? The kernel, okay. So we want to prove that the kernel is a subspace. So notice T of 0V is equal to 0W, which implies that 0V is in the kernel. Why? Remember, T is a linear transformation. This is using as T is linear. So we have T of the zero vector in V is equal to the zero vector in W, so 0V is in the kernel of T. Now suppose U, comma U1 are in the kernel of T, and A is a real number. Then, if we look at T of U plus U1, this is T of U plus T of U1, which is the zero vector in W plus the zero vector in W, because remember, U and U1 are in the kernel of T, and this is 0W, and this tells you U plus U1 is in the kernel. Similarly, T of AU is ATU, which is A times the zero vector in W. This again gives you the zero vector in W, which implies that AU is in the kernel, completing the proof. Any questions about that? Okay. The dimension of the kernel has a special name associated to it. It's called the nullity of T, and is denoted by nullity bracket open T bracket closed. The dimension of the image is what is known as the rank of T, and is denoted by rank T. Now, if I give you a linear transformation R3 to R, given by T of A, by the way, it's supposed to be R3 to R3. I don't know why it says R. It maps A comma B comma C to A plus B, B plus C, A plus C. Now, I'll leave it to you on your own time to show that T is a linear transformation. For now, you can take it for granted. What I want you to do is find its kernel and its image. I'll give you guys 5 minutes to work on that. I won't put you into groups since we find it better this way, and then we'll take up the answer. So it's 11:15 now to 11:20. I want you to just find its kernel and its image. The linearity portion, I'll leave to you to do on your own time. Okay. Can anybody tell me what the kernel of this map is? So remember, by the way, just when you're starting out, just remember what the definition of the kernel is. The kernel of T by definition here would be A comma B comma C in R3 such that T of A comma B comma C is the zero vector. Now, if I rewrite this, this is saying A plus B, B plus C, A plus C, or equivalently, so in other words, I have that A equals minus B, B equals minus C, and A equals minus C. So if I plug these into here, so remember, A was minus B, but B is minus C, so A is just C. If you just do double substitution. And B is minus C, and then you have C here. In other words, this is the span of is everybody clear of how this worked? By the way, sorry, I wrote this incorrectly. Yeah, so A, that definitely is not this. Hold on, there's a mistake here because there's a condition that forces the first coordinate to be 0. My apologies. That's horrible. This is why on Zoom it's so hard sometimes to do this. I should write it this way. A is minus B, but then this is minus minus C, so this is C. So A is equal to C, but simultaneously the third condition says A equals minus C. So we get minus C equals C, which implies C equals 0. But as soon as C equals 0, A and B become 0 because of these three conditions. So sorry, the kernel is, my apologies. Everybody clear on that? My minor mistake there. Okay, good. So that's the kernel of the map. And now we want to find its image. So the image of the map are the set of all possible outputs we can get. So the question is, what is its image? So one of the ways you can think about this is if you look at T of A comma B comma C, this is A plus B, B plus C, A plus C. Now isolate where the A's occur. So this becomes A times 1, 0, 1. Then where the B's occur, 1, 1, 0. Then where the C's occur. So the image of T is the span of these three vectors. Now you can check, by the way, that these three vectors are linearly independent. So this is actually equal to R3. Because I have three vectors that are linearly independent, dimension of R3 is 3. And from theorems we learned before, if you have n vectors in an n-dimensional vector space and it's linearly independent, then it also automatically spans your space, which means it gives you the entire vector space. Okay. Given an n by n matrix A, image of TA is the column space of A, and the rank of TA is just the rank of A. Remember, TA, just in case you've forgotten, TA is defined as the one multiplication by A. Now, to see why this is true, that's what I wrote on the original line area. I factored out the A, the B, and the C's in the coordinates. You're welcome. Now, to see this, if you write A in its column form, C1, C2 to Cn in terms of its columns, then the image of TA, which is AX, X in Rn, if you do the multiplication, matrix multiplication automatically gives you that AX is precisely XI, where, by the way, I've written X as a column here. Times the ith column of A. And that's precisely the definition of the column space of A. So this is where this definition of the image of TA being the column space of A and the rank of TA being rank of A comes from. Or not definition, it's actually the theorem that follows from this proof. If we define P to be the linear transformation that sends n by n matrices to n by n matrices via, it sends PA to A minus A transpose. We've already seen that this is a linear transformation. This I did before. What do you think its kernel is? What are the matrices that under this linear transformation will go to the zero matrix? Exactly. This is the symmetric matrices. And the image of P, sorry, as it is written in here, is the skew symmetric matrices. Exactly. A transpose equals A, which is symmetric. And if, by the way, to see, by the way, why the image is skew symmetric matrices, look at PA transpose for a second. This is A minus A transposed, which becomes A transpose minus A, which is minus A minus A transpose. In other words, all the matrices in your image have the property that their transpose is equal to their negative. And these are known as skew symmetric matrices. Any questions so far?
Quick question. How come you decided to, what made you make P of A into the transpose?
It's not that it makes me do that. I'm just when I was looking at this image, A minus A transpose, because of, I guess, my experience, I right away realized that if I take the transpose of this A minus A transpose, what I'm going to get is it's negative.
Okay, I see. Thank you.
So right away I realized, okay, that I'm looking at the skew symmetric matrices for the image.
Okay, I understand. Thank you.
Well, what are the matrices that go to, so if P of A equals 0, then A minus A transpose equals 0. A matrix is in the kernel if and only if P of A is 0, which is equivalent to saying A minus A transpose is 0, which is equivalent to saying A equals A transpose, i.e. A is symmetric. Okay. Yeah, always remember the kernel is the set of inputs that under the linear transformation go to the 0 element in your code domain. You're welcome. Okay, one thing you guys should realize, I've worked with this stuff a long time, so I have a tendency occasionally to go too fast. If I do, feel free to slow me down. I will not take offense to it. I promise. And I apologize in advance if I go too fast. But it's your job to slow me down. Is that fair enough with everybody? So I'm telling you that now. A linear transformation. Okay, fair enough. Good. A linear transformation T from V to W is said to be one-to-one or injective. And this is something from Math 102, it carries here, if it satisfies the following property. If T of V equals T of U, then V must equal U. In other words, no two distinct inputs will go to the same place under T. Prove that a linear transformation TV to W is one-to-one if and only if its kernel is trivial. So I'll give you guys about 5 minutes to prove this. You should go in each direction, and then we'll take up the answer. Okay, so if we want to show this, how do we approach this question? Any ideas? Anybody? So pick a direction. Which direction do you guys want to go? I'll do one of them and I'll leave the other for you to do as an exercise. You want to go left to right or right to left?
You go right, like right to left.
Okay. So like this? Did I pick that correctly?
Yeah, sure.
Okay. All right, sounds good. Okay, so I have that the kernel is 0. I want to prove that it's 1-to-1. So suppose T of U equals T of U1. Then T of U minus T of U1 equals the 0 vector in W. But this implies that T of U minus U1 equals the 0 vector in W, which implies U minus U1 is in the kernel of T, which is the 0 vector in W. But this says U minus U1 equals the 0 vector, 0 vector in V, not W. This is in the subspace of V. This says U equals U1. Hence, T is 1-to-1. Questions? Everybody okay with this? That's the definition of being 1-to-1, Aditya. Above line. I've proven yeah, I just wrote the number instead of no, 1-to-1, injective. I just wrote the number 1 instead of the wording. So sorry about that. My apologies. Sorry about that. Okay. So let A be an invertible matrix and define T to go from m by n matrices to m by n matrices via T of x equals AX for all x and m by n matrices. First of all, T is a linear transformation. And the question is T 1-to-1? And is it onto? So the fact that it's a linear transformation, if you look at T of x plus y, this becomes AX plus y, which is AX plus AY, which is T of x plus T of y. And if you take a constant, so that proves this portion. The question is T 1-to-1? I'm not going to let you work on it, but I'm asking, what do you guys think? So whenever you want to show 1-to-1, you start with, okay, suppose T of x equals T of y. If it's 1-to-1, what do I need to show if I think it's 1-to-1?
That x equals y.
Exactly. I need to prove, if I think it's 1-to-1, I should be able to prove x equals y. Well, what does this tell me? It tells me ax equals ay. This is where this comes into play. Because it normally, by the way, I emphasize this a lot. If A is not invertible, this will not necessarily imply x equals y. But because A is invertible, I can multiply both sides by A inverse. Now the left side becomes Ix, the identity matrix times x. The left-hand side is Ix, the right-hand side is Iy, which says x equals y. Be very careful here. Invertibility is essential in this part of the proof. A lot of times I see in this course that people say, oh, AB equals AC. This says B equals C. This is false for matrices in general. In fact, if A is not invertible, there are infinitely many B and C's that are not equal, but AB will equal AC. So this does not hold in general. It does hold when A is invertible because of what I just did. Everybody clear on that? Please ask away if you have a question about that. Yes, absolutely. Yes. If it's invertible, I'm saying this is in general not true. But if it's invertible, then B will equal C. The exact same proof that I just gave with X and Y will prove B equals C. Now, for onto, what do? For onto, you say, okay, you pick something in the codomain. Suppose Y is in my codomain and domain are the same here. I need to come up with an input that goes to Y. What input do you think I'm going to pick? What input can you put for X that when you apply T to it, you get Y back? Looking at this X here, T of X. What do I put inside here such that I know my answer will be Y? Exactly. Then T A inverse of Y will give me Y. So T is also onto. Everybody clear on that?
Could you go over onto again? I'm still a bit unsure on how you managed to get to the conclusion.
But okay, so this is for Math 102. If we have F going from A to B, this is called onto if for all B in B, there exists A in A such that F of A equals B. In other words, for any output you pick, there is an input going to that output. That's what onto means. So here I say, okay, pick a point in the codomain. I'm calling it Y. I'm showing you there is an input going to it.
Okay, I see what you mean. Okay, thank you.
Yeah, there's so many students I won't say for some reason, it's obviously there's something to it. So many students have a trouble with onto, and it takes quite a bit of practice. So don't feel like you're the only one. In 102, it's a nightmare to teach, and I think it continues. Just remember, onto means you're hitting everything in your codomain, which means that if I pick anything in the codomain, there must be an input going to it. That's what I have to prove.
Okay, I see. Thank you.
Yes, surjective is the same terminology as onto. Okay. Now let A be an m by n matrix and let TA be the linear transformation given by TAX equaling AX. Then the following holds. T of A is onto if and only if, or surjective, if and only if the rank of A is equal to the dimension of the codomain, which is M. Moreover, T of A is 1-to-1 if and only if rank of A is N. It's the dimension of its domain. And one of the really nice prop theorems is what is known as the dimension theorem. If T goes from V to W is a linear transformation, and we know the kernel has finite dimension and so does the image, then the dimension of V is finite, and it is the sum of these two dimensions. No, that's not, I do not want to bring guns and things into this. But okay. So the dimension theorem is unbelievably important, and it plays a very crucial role in a lot of linear algebra. And basically it's telling you that the dimension of the domain is actually equal to the dimension, the nullity plus the rank. And that's another way of writing it here. If S is equal to R3 to R2 is given by S of A comma B comma C equaling A plus B, A minus B, verify that this is a linear transformation and that 3 is equal to the dimension of the kernel of S plus the dimension of image of S. This I will leave to you to do, but it's a good practice exercise for you guys to do for yourself. Find the kernel of S, find the image of it like we did before for another question, and then verify that whatever you found, their sum will be the number 3, which is the dimension of the domain R3. Now, this is where we get more back into the theoretical aspects of this. Suppose that T goes from V to W is a linear transformation, and we are given a basis V1 to VR, VR plus 1 to Vn is a basis for V, such that the vectors VR plus 1 to Vn is a basis for the kernel of T. Then the following holds. Automatically, the first R vectors, when you apply T to them, they will form a basis for the image of T, which consequently tells you that because there's R of them here, that the rank of T will automatically be R. So if at any time you pick basis for V such that some of the vectors are a basis for your kernel, then the rest of the vectors will automatically be a basis for your image. And a consequence of this theorem is if T goes from V to W is a linear transformation and V is finite dimensional, then the dimension of the kernel and the rank of T are both less than or equal to the dimension of V. This is also a consequence of the dimension theorem, because the dimension of V is the sum of these two things. So each one has to be less than or equal to it. Remember, dimension and rank cannot be negative by definition. So here's a place where I'm going to show you how these get applied. Remember the differentiation map. We already know that this is a linear transformation. We're going to compute the kernel of D and conclude that D is actually onto. How do we do this? Because what is P prime X being 0? It means that P of X must be a constant. So in other words, the dimension of the kernel of D is 1. Why? Because P of X, to be in the, so this portion, and this tells me that the kernel of D consists of only constant functions. By the way, how would I write this as the span of what? What would I put in here?
1.
You could put any non-zero constant, in fact, but 1 will do. And as you can see, remember, this is linearly independent. Why? Because it's non-zero. So this tells you that the dimension of the kernel of D is 1, because there's one vector in its basis. So we have the dimension of kernel of D is 1. Now we use the dimension theorem. The rank of D is equal to, by the dimension theorem, a dimension of Pn minus the dimension of the kernel of D, which is dimension of Pn is n plus 1. Dimension of kernel of D we just found is 1, which is n, which is equal to the dimension of Pn minus 1. In other words, rank of D is exactly the same as the dimension of the codomain. But remember, the image is a subspace of Pn minus 1, and they have the same dimension. By theorems we did before, this means that they are equal to each other. And by definition, if the image is equal to the entire codomain, then the map must be onto. So this is where the dimension theorem can be used to very easily conclude that a map is onto, because you know that the image of the map sits inside your codomain. So if you can show their dimensions are the same, you've proven that the two actually are equal to each other, that is, the image is equal to the codomain, and hence it is onto. Let me erase this. A linear transformation TV to W that is also a bijection is called an isomorphism. So linear transformations that happen to be also bijections are called isomorphisms. Two vector spaces V and W are said to be isomorphic, written with this notation V kind of equal with the squiggly sign above, if and only if there exists an isomorphism between them. By the way, this portion, you have to be very careful. When we say two spaces are isomorphic, we mean there is an isomorphism between them. We don't mean every map must be an isomorphism. Everybody clear on that? In fact, you should convince yourself that every space is isomorphic to itself. What map would I use to prove that a space is isomorphic to itself?
The identity?
Exactly. The identity map so R is isomorphic to R, but the map F going from R to R given by f of x equals x squared is not an isomorphism. Why? It's not injective, and it's certainly not surjective. F of -1 equals f of 1, and you don't even hit the negative numbers. But R is isomorphic to R because there exists an isomorphism between R to R, namely the identity being one of them. So this word exists, you should really pay attention to it. It's telling you there's at least one isomorphism. So what does it mean when I say two spaces are not isomorphic, do you think? Exactly. So not being isomorphic means if you pick any map from V to W, that map cannot be an isomorphism. So here are some examples of isomorphisms. The identity we just did. In fact, the transpose map is an isomorphism from M by N matrices to N by M matrices. The map given by the one that sends the 2 by 2 matrix A, B, C, D to A plus BX plus CX squared plus DX cubed. This is an isomorphism. And like I said before, notice that V being isomorphic to W says that there only exists a map from V to W or vice versa. It does not say that every linear transformation must be an isomorphism. And this is the example f of x equals x squared that I just wrote down. If V and W are finite dimensional spaces, the following conditions are equivalent for a linear transformation. T being an isomorphism, by the way, these are really important because it gives you a very quick way to check if a map is an isomorphism instead of going through bijection checks and everything. T being an isomorphism is equivalent to saying that if you have any basis of V, then when you apply T to that basis, you get a basis of W. Now, this seems tedious because you would have to check for any basis. But the next example says, if there exists a single basis that does this, then it's automatically an isomorphism. So a really nice way to check if a map is an isomorphism is all you need to do is pick a basis for your domain, apply T to it, and see if you end up with a basis for W. If you do, you have got an isomorphism. If you don't have an isomorphism. And since I know a lot of you hate onto, this is one of the ways you can avoid checking onto. By the way, you shouldn't hate it. If you're scared of it, get over the fear by practicing it. But this is a way around it. And a theorem, consequently, is if V and W are finite dimensional, then V is isomorphic to W if and only if their dimensions are equal. Why? I can just send basis to basis automatically. If you see this, all I do, if V and W, if say E1, E2 to En is a basis for V, and F1, F2 to Fn is a basis for W, then I can force a linear transformation with T of EI being Fi. I could define T this way. Remember, we can always define a linear transformation from one space to the other. We were doing that before when I said there exists a linear transformation always. And this becomes an isomorphism because I've forced the basis to go to basis. Not force, I've constructed it that way. That's a better word to use. So consequently, it follows that if the dimension of a vector space is n, then it must be isomorphic to Rn because the dimension of Rn is n. Okay, I'll stop there and I'll give a 10-minute break and then we'll start the second half of the class. Okay. So if you have, if V denotes the set of all 2x2 symmetric matrices, we want to find an isomorphism that goes from P2 to V such that T of 1 equals I, where I is the 2x2 identity matrix. So remember, we want to go from P2, which is the set of all polynomials up to degree 2. And remember, the dimension of 2x2 matrices, symmetric matrices, we did this before, is 3. So there should be an isomorphism between P2, which has dimension 3, and V. And the way we do this, we use the basis 1x and x squared, which is the basis for P2. Oh, I've gone. So if I define T of 1 to be I, the question is, what do I define T of x and T of x squared to be? Does everybody remember we did a question where we found the basis for V before? And I'm not sure why can everybody hear me? My screen seems to be frozen. I can't, the mouse is not working. I'm not sure what to do. I can't even check the chat. Can anybody use the mic, please?
We can hear you loud and clear.
You can hear me loud and clear. Okay. My screen is frozen and the pen is not working. I don't know whether you guys can see. I'm trying to write.
We can only see the frozen screen.
Yeah, it's frozen.
Yeah. Okay. So I'm going to have to turn off my computer and turn it back on. So I suggest you guys will probably get kicked out. Come back on. Give me a couple of minutes.